Hello, F block. While I'm out at my meeting, we're going to start the notes on section 5.2, and when I get back, we'll stop the video and you'll get the rest of class live. What we're going to look at is integration now involving the natural logarithm. So again, this is section 5.2. Last time we looked at the derivative of the natural log. This time we're going to be looking not at the integral of the natural log of x, that's a little bit more involved, we're going to save that for the end of the year, but rather integration that gives us the natural log of x. The first thing we need to realize is the integral of 1 over x dx. Me asking you the question, what has 1 over x dx as its derivative? Well, we know that that's the natural log of x. So we're going to say the natural log of x plus a constant. But I need to kind of watch domain things over here. The domain of 1 over x is everything except for 0. So I need an answer whose domain is everything except for 0. So I'm going to say rather than just the natural log of x, I'm going to make it that more general case that we saw last time and say the natural log of the absolute value of x plus a constant. One other thing that I do want to note, though, this integration rule is really just a special case of the power rule, when the power happens to be -1. So I also just want to rewrite our power rule, the integral of x to the n dx is x to the n plus 1 over n plus 1 plus a constant if n does not equal -1. That's our normal power rule. Add 1 to the power, divide by the new power. And if the power is -1, that's where we're going to get our natural log of the absolute value of x plus c from, if our power is -1. So please make sure you have those two rules in your notes. Then we're going to look at some more straightforward examples of integration with our natural log, and the rest of today will just be some variations on that. For our first example, we're going to do the integral of 10 over x dx. That 10 isn't helping anything. So I can move that out front by my constant multiplier rule. This is not u substitution. This is, again, just constant multiplier rule. You should be able to convince yourself that these two things are the same. Well, now I'm exactly in my form to be able to integrate, and I'm going to get 10 times the natural log of the absolute value of x plus a constant. And that's our answer. Although we could do a little bit more work with this, I could take that number up front, and by my properties of logarithms, I could make that into a power inside my log. I could say the natural log of, well, if you raise x to the 10th, that thing is always positive, so I don't even really need the bars there. And I could say the natural log of x to the 10th plus a constant. Either of those would be acceptable final answers. However, if we had like a multiple choice question, this answer might not be there, and this one would be. So we need to be able to convert between the two forms using our properties of logs. Next one. Let's look at the integral of 1 over 2x plus 3 dx. The integral of 1 over 2x plus 3 dx. Now, we've got to realize we're doing integration here, so we shouldn't be thinking about product rule, quotient rule, chain rule. Instead, we should be thinking about, is there any algebra I can use? No, there isn't. Or the biggest trick for integration is u substitution. And that's what I'm going to have to do in this problem, a u substitution. I'm going to make u the entire denominator. I'm going to make u 2x plus 3. Well, quickly go calculate your du. That should be 2 dx. And I can make that work by taking my original integral. I can multiply inside by 2 and cancel it out front with a 1/2, which is going to give me 1/2 times the integral of du over u. It's now exactly in our form. By the way, du over u, that's the same as 1 over u du. It's exactly in our form to be able to use our rule that gives natural logs. So see if you can finish this one off. One half times the natural log of the absolute value of 2x plus 3 plus a constant. I could make the 1/2 into a power, but since 2x plus 3 isn't always positive, I do need to include the absolute value bars, so I could say the natural log of the square root of the absolute value of 2x plus 3 plus a constant, but I think just leaving the 1/2 out front is also okay. Let's take a look at the integral of 3x squared plus 1 over x to the third plus x dx. We're going to try a u substitution. So one of these two parts is probably u. How about you take a moment? See if you can figure out u, calculate du, and see if you can go from there. Well, I'm going to make u the denominator because du, its derivative, is actually exactly what I have up top. And by the way, you can never really have a du on the bottom. We can't integrate 1 over du or something like that. So I think this u substitution will just give us 1 over u du. If you haven't finished, go finish that problem. Again, I do need to include the bars because this thing isn't always positive, so I need to make sure it is. Natural log of the absolute value of x cubed plus x plus a constant. Okay, 2 more and then we'll start getting into some variations. Let's take a look at, okay, this one's a little strange. The integral of 1 over x times the natural log of x dx. The integral of 1 over x times the natural log of x dx. We don't know how to integrate the natural log of x, so somehow our work will have to deal with that fact. We're going to need a u substitution here. Take a moment and think, and see if you can figure out what u would be and what du would be. I don't know how to integrate the natural log of x, but if I say u is the natural log of x, its derivative, 1 over x dx, that shows up over here. This whole thing, that's my du, and I've got the integral of u over du. Go from there. A little strange looking, but I also feel like last night you saw like a derivative of a natural log inside another natural log. We're going to get the natural log of the absolute value of the natural log of x plus a constant. See what you can do with the integral of 1 over the square root of 2x plus 1. See what you can do. I have a little bit of an issue here. I did my u substitution. U is 2x plus 1. Du is 2 dx, 2 in, 1/2 out. I've got this integral. I know how to integrate du over u. That's my natural log. But what if it's du over the square root of u? What do we do for du over the square root of u? Have you realized that we could have handled this problem before? This is just straight u substitution power rule stuff. This is really just integrating u to the negative 1/2. Our natural logs are a special case of the power rule when the power is negative 1. The power here is not negative 1, so it's just a regular power rule problem. Go finish it. Square root of 2x plus 1 plus your constant. So the homework tonight's going to start with some straightforward-ish problems like the ones we saw. Usually the trick is just use a u substitution. Usually u is what you have in the denominator, and hopefully its derivative shows up top. If we have a natural log in our problem, somehow that's probably going to be involved with the u. Realize if we have du over anything more involved than just u, it's not natural logs, it's just old power rule stuff. The first variation we need to look at involves integrating certain types of rational functions. Actually, why don't I just write it down first? You don't have to bother copying this down at this point. I just want to show you what we're going to deal with. X squared plus x plus 1 over x plus 1 dx. Again, no need to copy it down. Just watch. If we make u the numerator, then du is 2x plus 1, vaguely sort of what I have in the bottom, but not really. Plus, I can't have du in the bottom. Just a straight u substitution isn't going to work on this. What I need to do is a little bit of algebra to rewrite this problem in a better form that I can handle. I am always going to use this algebra I'm going to show you in a moment when we try to integrate a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. And what this method is, this goes back to something you learned in Algebra 2, we're going to use some long division to rewrite this problem. Okay, so I'm assuming that everyone just groaned. If you haven't, go do that right now. Just get it out of your system. And then we'll go review our long division. Integrating using long division as a first step is what we're always going to do to integrate a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. This is to integrate a rational function where the degree of the numerator, I'll kind of use function notation here, is greater than or equal to the degree of the denominator, like that example I showed you. And now I think we can go and write that one down. We're going to go do the integral of x squared plus x plus 1 over x plus 1 dx. We're going to start by using some long division to rewrite this problem, because that is what we are always going to do when we want to integrate a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. So I'm going to ignore the calculus part for right now, and I want to use long division to rewrite this. I'm going to say x plus 1 divided into x squared plus x plus 1. Yes, you could do synthetic division, but long division will always work. I'm going to show you an example in a moment where there's no way around long division, so we might as well just see how to use it for everything and review this method. Remember, with long division, we divide, then we multiply, we subtract and bring down, and then we restart the process. I'm going to do my division. I'm going to divide x squared by x, and x squared divided by x gives me x, my first division answer. I'm going to write that above the x term. I've got an x over there. I've divided, and now I multiply. I'm going to multiply that answer times both things out front. That's going to give me x squared plus x. I'm going to put some parentheses in and subtract. And in this case, looks like the first two terms canceled. Usually just the first term cancels. That's okay. Those are gone. I'm going to bring down my next term. I'm going to try to restart my division, but I can't. I can't divide 1 by x, which means I'm done, and I have my remainder of 1 over x plus 1. Well, trying to integrate that, let me try this again. This answer is algebraically equivalent to the first problem that we had. So rather than trying to integrate that original problem, instead, I'm just going to integrate x plus 1 over x plus 1 dx. Well, part of it is straight integration. Part of it requires a u substitution. So I'm going to go and split this into two different problems. I'm going to say the integral of x dx, didn't need those parentheses, plus the integral of 1 over x plus 1 dx. I'm going to set up my u substitution and say that u equals x plus 1 and du equals dx, which will make this the integral of x dx plus the integral of 1 over u du, or of course just du over u. I'm going to go and integrate x squared over 2 plus the natural log of the absolute value of u plus a constant, which gives me an answer of x squared over 2 plus the natural log of the absolute value of x plus 1 plus c. I want you to try one of these problems. I'd like to see what you can do trying to integrate Let's do 2x cubed plus 5x squared minus 10x plus 4 divided by x squared plus 4x. How do you know we need long division? Hopefully you noticed the degree of the numerator greater than or equal to the degree of the denominator. So long division, to rewrite it, is the first step. Go do your long division. This is a problem where there's no way around the long division part. Synthetic doesn't work for quadratic division problems. See if you can do the division. And then, of course, when you're done, that's just rewriting the original. Then we need to integrate. See what you can do. Okay, I'm done with my first round of division. Actually, maybe I need to bring down the 4. I'll save that. And at this point, I can't divide anymore. So my remainder will be this. Finish off the problem, please, and go integrate that thing. Convenient, but that's exactly what I had up top. that should be our answer. And by now, I really should be back from my meeting. If for any reason I'm not, do some work on that midterm review packet, but I'm pretty sure I'll be back by now.